Okay, so we're going to talk about the energy level structure of atoms. And what we're trying to get at here, where we're going eventually with this, is we are going to this sort of thing. We're going to learn how to do this kind of notation that you've seen a little bit of at this point. And we're going to try to understand that more fully. But first, we want to talk about a little more about electrons in atoms. Electrons in atoms can be described by 4 parameters. Parameters, you could say properties. In other words, if you were an electron in an atom, there would be 4 things about you that mattered, and only 4. If you were an electron in an atom, there would be 4 things about you that mattered. All right? So the first of those 4 is called the principal energy level. The principal energy level is basically this idea here. So let's put a line here. We're going to make this a table. This is the Bohr model energy levels, essentially. So, and what we're talking about here then is N, the N level. N is equal to 1, N is equal to 2, and so on. The Bohr energy level. So maybe we'll draw a little atom here. This is a nucleus. And it's what we think of like this. Nice drawing in your book on page 380 of this thing. Hopefully you've taken a look at that. That's what we're talking about. So the principal energy level. All we're doing here is we're putting another word on here called principal. The word principal, because we're going to start to talk about other kinds of energy levels. So the principal energy level is the Bohr model energy level. And this is related to distance from the nucleus. It's related to distance from the nucleus. In other words, the higher the value of N, the further you are from the nucleus. Whoops. So the symbol is N. That's the symbol for the energy level. And the principal energy level, it can be like 1, 2, 3, and so on. And so the idea here is that 2 is further out from the nucleus than 1, and 3 is further out than 2, and 4 is further out than 3, and so on. In terms of energy, if I say increasing energy from left to right, then it goes like this. Basically, you have more energy. The higher the N value, the more energy you have. So that's just kind of a summary of this parameter, this property of you as an electron. You can talk about, if you were an electron, you might talk to other electrons and you'd be like, hey, what's your energy level? What's your principal energy level? I'm a 4, what are you? Right? So that is what we're talking about here. This is one of, remember, there's only 4 things about you that matter. Life would be so simple, wouldn't it? If there were only 4 things about you. But this isn't quite as simple as that. But what's the next thing? It's called sublevel. Now it turns out here that the principal energy levels are subdivided. So sublevels are subdivisions of the principal energy levels. By the way, this is principal, it's LE, right? Did I write AL up there? I think it's principal. I think principal with an A, L is like Mr. DiLoretto. Yeah. So principal energy levels are subdivided. You can think about it like this. Like, so instead of them just being like n equals 1 and n equals 2, what happens is the 2 is subdivided into sublevels that are closer to each other than they are to the next principal energy level. So there's subdivisions in the principal energy level. And they are related to the shape of the region occupied by the electron. They're related to the shape of the region occupied by the electron. Their symbols are like this: S, P, D, F, etc. I say etc. because in a ground state atom, an atom that's not being excited, like an electric field or a flame or something like that, you're not going to go any higher than F. So S, P, D, and F. And that might look a little bit familiar to you because of this sort of thing. That's the S and the P that are showing up here. Those are the sublevels. So S, P, D, and F are the sublevels. Now how does this work? Well, first of all, in terms of energy, it goes like this. Increasing energy, we go from S, P, D to F. So in a given sublevel, in a given principal energy level, a D has more energy than an S, and an F has more energy than a D, and so on. Now let's look at this kind of graphically, how this works, this subdivision thing. So I'm going to scroll down here, and what I'm going to do is write my principal energy levels in this kind of order like this, just up to number 3. Remember that N is the symbol for the principal energy level, and so this is energy going up on this side like that. Now it turns out that principal energy level 1 has only one subdivision. In other words, it's not subdivided. It's not subdivided. So it only has one sublevel, which is an S sublevel. So it has only one sublevel. This is a little confusing. I guess maybe a better way to say this would be that it is its own sublevel. In other words, there's no subdivisions. But we do talk about an S, one S. So in the first energy level, and here's how to look at it. Now you have two things to talk about with your atom friends or your electron friends. Not only can you say, hey, what principal energy level are you? I'm a 4. You can say, what sublevel are you? Oh, you're a 4 too? What sublevel are you? And then they might say, oh, I'm sublevel S. Oh, okay, I'm P. Or I'm D. So see, there's subdivisions. So within principal energy level 4, you can have different sublevels. Here's the thing. If you talk to somebody and you said, what principal energy level are you? And they said 1, you would say, oh, so you're an S. Because you would know they're an S because there's only one subdivision, an S. Now let's look at n equals 2. In n equals 2, there are two subdivisions. There's an S and there's a P. And the p is a little bit higher energy than an s. And in n equals 3, there are 3 subdivisions. S, P, D. Guess how many subdivisions there are in energy level 4? 4. Energy level 5? 5. Energy level 6? 6. Energy level 7? 7. So this is a kind of it's a kind of a splitting that happens. Think about this. As the energy goes up, they split out into more possibilities. There's more options. As you get more energy, you get more options, folks. There are in excited atoms. So like, say that thing there, that the power supply we had where we put the different gases in and they lit up, you can get higher than F in those kinds of circumstances. In ground state atoms, you only see up to F, and when we're writing out our configurations 1s2, 2s2, we'll never get higher than F. So I'm not drawing level 4 in here, but if I did, it would have 4 branches, and it would go S, P, D, and F. Now, they are related to the shape of the orbital. So here's how that works. If you are in an S, then the area that you occupy has a spherical shape. This is the classic picture of an electron in an atom moving in kind of a circular area around the atom, a sphere. But if you were in a P sublevel, then you would be moving about in a kind of dumbbell-shaped region. Double teardrop. So you would have this kind of... Now, by the way, this does not mean that you are in a figure 8 pattern, that you're like skating around the atom in a figure 8. This means that the area that you're found in has this kind of a dumbbell shape. If you're in a D, then it's got kind of a clover shape. Now, I think you can see that you can kind of get a feeling for how the energy going up would make the pattern more complicated. Can you see how an electron going around in here has more energy than an electron going around in a sphere? See what I'm saying? So we're turning up the energy here as we go between these. Now, the thing to keep in mind, though, is level 2 also has an S-shaped sublevel. And it also has the dumbbell shaped, but it does not have a clover shape. It doesn't have any electrons with clover shape. Yeah. F has 6 lobes generally. But what I want to point you to for this is your book, because the drawings get pretty complicated. And so we want to look in your book for this on page 365 for some better drawings. Now, so think about this. The splitting, as we increase energy, they get more splitting. They're more subdivided. Your options are great. It's like this. Let's say you set some goals for yourself, and then you achieve those goals. What happens? You get excited. That's true. Good. But more options open up for you. More options open up for you. More opportunities. And then if you take advantage of those opportunities, of those options, then more opportunities open up for you. Right, and you get more excited. So further success, each step of success opens up more options, more opportunities. That's kind of how it is for electrons. Okay? Unfortunately, electrons have a way of always getting sucked back down to the lower energy level. Okay, so what's next? Let's go back up here to the top. And the next property of you as an electron is called your orbital. Now, I want to point something out before I go any further. This is what Salman Khan was focusing on, the orbital. And he was taking a much different approach than I'm taking to this concept. He kind of started with orbital and then worked his way to the other things a little bit. But the orbital can be thought of as in a couple different ways. One is subdivisions of the sublevel. So you can think about it as subdivisions of the sublevels. By the way, subdivisions by Rush, the classic rock band Rush, is one of the best songs of all time. And so if you have never checked that out, go on YouTube and check out Rush Subdivisions, one of the coolest songs of all time. Yes? We'll see how it goes. Let's put it that way. We're going to see how it goes, and then we'll decide whether this is going to go public or not. Yeah. Well, the other chemistry A, I don't think, did I? So the other class, I mentioned this before, they're literally like 3 periods ahead of you guys after this week because they have so much more time. So they decided to do a dance for the electrons. We'll see. I'm not sure yet. Yeah. So we'll see how it works out. The second way to think about the orbital is the actual area occupied by the electron. Now, one thing I want you to kind of think about as we're going through this is I've been kind of talking about the electron as a particle, sort of, today, but you could do the same thing thinking about it as a wave. So maybe the electron's just a wave, just a vibrating piece of energy. And you could think about it either way. So the actual area occupied by the electron is the orbital, and this is the way that Salman Khan was talking about it. It's the region of space where you would find the electron. That's the Now, how is that different though from what we said before? Well, it's different from the sublevel because it's related to the orientation of, so related to the orientation of the area occupied by the electron. So in other words, we're adding one layer, not just the shape, but how is that shape positioned in space? So for example, how about the symbols? Here's what we'd be looking at. Something like this: P sub x, P subscript y, and P subscript z. Now what does that mean? It means that if I have a P sublevel, so let's bounce down to here quickly. It turns out there's 3 different P orbitals. I was making 5, sorry. There's 3 possible P orbitals. There's the P along the x-axis, P subscript x. There's the P along the y-axis, P subscript y, and there's P along the z-axis coming out of the board here like that. Is that usually the z coming out, or is the z vertical? Z is coming out? Yeah, so the z is coming out at you. So in other words, you can have P along this axis, P vertical, or P coming out at you. So there are 3. So I'm talking to my electron friend that I just met, my new friend, and I say, so what principal energy level are you? And this person says, this electron says, I'm energy level 3. And I say, really? So am I. What sublevel? P. No way. So am I. P. Which orbital are you? Now this friend says P sub x. Oh, I'm P sub y. Now here's the good news though. The good news is, in terms of energy, P sub x equals P sub y, which is equal to P sub z. And the reason that's good news is because it means that I, as an electron, can easily and instantaneously switch to another orbital in the same sublevel with no energy cost to me at all, which means it can happen spontaneously and all the time. So I'm really not disappointed, because when my new friend says, "Oh, I'm P sub X," I actually should say, "Awesome, I'm P sub Y. I'll come over sometime." Because we're at the same energy, you don't have to add any energy into the system to make that move. Okay? They're equivalent. Now, for S, there's only one orbital. It's just S. How many ways can you orient a sphere? One. Now, the D has 5. And I'm not even going to try to draw them. Page 365. Do take a look at it, though. They all, what it is basically they're all clover shapes like this, all except one, but they're just in different planes. So like this plane, this plane, this plane. So they're in 4 different planes, and then plus there's one weird-looking one. So basically you have 4 different clover shapes plus one that looks like some kind of futuristic space station or something. It has like a P sublevel with a ring around the middle. So those are orbitals, and the energies are all equivalent. By the way, this one would also have 3 orbitals, the P, and this one would only have 1. Yes?
So the orbitals are just like where we think the electron would be?
Yes. Yep. So notice they all have the same shape. So all the P orbitals have the same shape. They all have the same energy. They're just oriented differently in the atom. And there are 3 distinct regions of space where you might find an electron. It's either going to be here, here, or here. Okay? There's 3 options if it's in a P sublevel. By the way, and I think Salman Khan brought this out pretty clearly, but if this were the case, so it doesn't mean you're going to be on this curve right here. It means you're going to be somewhere in these regions. And it's random. Where you are at any given time is going to be random. All right, let's look at the next. The last thing you can talk about is the spin. Well, you don't need a lot of spin. You don't need a lot of room for spin. It's pretty simple. This is the last one. Yep. For a spin, you'll be glad to know there are only 2 options, and they are always the same. They are spin up, which has the symbol up arrow, and spin down, which has the symbol downward arrow. And basically what we're talking about here is there is a property of an electron that when physicists measure it, it is a magnetic field that you get when you have a spinning charge. So if you have a spinning charged particle, it generates a magnetic field. And electrons do this. Now they don't, it's weird because they don't really think the electrons are spinning, but they're doing something that is like they're spinning. And so this would be called up, and this would be called down. Now, they're actually spinning, say, clockwise or counterclockwise, but we call it up and down. And there's only 2 options. And in terms of energy, so the only 2 options are up and down, and in terms of energy, they're both equal. Now so at this point, before I go to talking about how I would discuss this property with another electron, I want to mention something called the Pauli exclusion principle. Very important. And it basically says that no 2 electrons no 2 electrons in the same atom, can have the same 4 properties. In other words, you can't have two electrons in the same atom with the same principal energy level, sublevel, orbital, and spin. Here's what that means. The consequence of this is that you can only have two electrons in every orbital, maximum of two. Why? Because there's only two spin options. And if you're in the same orbital, then you're automatically in the same sublevel and principal energy level. So if you're in the same orbital with somebody, you're automatically also in the same sublevel and principal energy level. Therefore, you have to have a different spin. And because there's only two spin options, there can only be two of you in an orbital at the same time. And you have to have opposite spins. Why? It just is. Yeah, it just is what it is. With quantum mechanics, it's basically, you know what this is? This is a chart of the rules of quantum mechanics. To ask the question why the rules are such as they are is to not get an answer. Because the answer is they just are. Now, where do they come from, though? That's a good question. Where do they come from? They come from the Schrödinger equation. So do you remember that crazy-looking equation with the psi symbol and the calculus and everything? That equation can be solved for each of these four parameters for any electron. So all of this stuff flows out of the mathematics. And it's like these kind of rules that govern the universe. Why are they like they are? I don't know. It's possible that there are a huge number of universes that all have different rules. And we just happen to be in a good one that has rules that enable us to be here. That's possible. Now, let's say, okay, so I'm walking down the street and I meet another electron. What principal energy level are you? And the electron says, I'm principal energy level 3. Fantastic. So am I. What sublevel are you? I'm sublevel P. Amazing. So am I. Which orbital? PX. No way. I'm PX too. What spin are you? Spin up. No, I wouldn't ask that question.
It doesn't matter.
Because I would know. Because if I'm spin up, then I already know that they're spin down. Because you can't have the same spin and be in the same orbital at the same time.
You guys can make it work.
What? Scroll up. Yeah. All right, now, so we have these four parameters, and what happens is this controls the numbers of electrons that can be in each energy level. Let me say that again. These rules control the number of electrons that can be in each energy level of the atom. For example, principal energy level 1 only has one sublevel, which has only one orbital, so principal energy level 1 can only hold 2 electrons. Principal energy level 2 can hold how many electrons? It can hold 2 in its S sublevel, and how many can it hold in its P sublevel? 6, because it has 3 orbitals, right? So total is 8, right? Now, yeah, draw what thing? Right, yeah, so if you've ever drawn like the dot diagrams where you have the rings and the points outside, the other thing I want to point out here, I'm trying to pull this up, is if you look at periodic table, maybe we'll finish up with that today. P can hold 6 because it has 3 orbitals. Each orbital can hold 2. Now, this does not mean that every orbital has to have 2 all the time. It can only have 1 also. An orbital could have 1 electron in it. It just can't have more than 2. That's what we're saying. Yeah, like hydrogen. Hydrogen has an orbital with only one electron in it.
You should ask Mr. Kate, is the electron hotel story?
Oh,
Is it good story?
You know what? I think I saw him. Oh no, it was Mr. Blomstrand doing something like that.
and don't bring Kate.
That was a great.
All right, look at this. Watch this, folks. This is important. And we're going, actually, next week we're going to talk about electron configurations and then the periodic table. It's going to lead us right into the periodic table. Why will it lead us into the periodic table? Look at this. Look at the first row. How many elements? 1, 2. Look at the second row. How many elements? 1, 2, 3, 4, 5, 6, 7, 8. Look at this. How come there's 2 over here and then 6 over here? These have their last electron in an S sublevel. These are filling their P sublevels. And because there's 6 electrons that can go into the P. Now, why would there be 10 columns in the middle? Yeah, there are 10. The purple is 10. What are those? Those are the D. Look at D. D has 5 orbitals, each of which can hold 2 electrons, total of 10 for a D sublevel. Now, what is this? What's going on with these 2 rows down at the bottom? Some of these are synthetic, not all of them. Uranium's not synthetic. A lot of them are synthetic, but look how many there are. What's going on here? These are the F. The F sublevel can have 7 orbitals. So it can hold 14 electrons. But you're right. See how this is supposed to be plugged into here? They pull it out because it would make the table too long to fit on the page. Now, it's a little bit spooky. You know what's spooky? Is that they had this basic shape before they knew about this 1s2, 2s2 stuff. Yeah, really. And it is not because someone spoke to them from beyond the grave that I know of. It's because what they were doing when they first made the table is they were lining up elements according to their properties. They're going atomic number order, and then they were arranging them so that elements with similar properties would be in line with each other. Makes sense, because if you have a similar electron structure, it makes sense that you would have similar properties. Remember, we started off the unit by saying that it's the electrons on the outside that are going to be the most important because they're making contact with the world, right? With other atoms. And so what we're going to find out as you look at the 1s2, 2s2 stuff is that they have the same electron configurations. The outer shell configuration is the same. By the way, I should mention this before I wrap this up, and that is that the principal energy level is also called shell. So you will see this word, and this is important because I'll use the word as well. You might see it. You might hear Khan talk about it and other people on the internet. It's called a shell. And I guess that's because instead of just being like a ring, it's more like a sphere. It's a smeared out sphere. By the way, I think to finish up, let's talk a little bit about well, maybe we should wait on that. Do you want to talk about the Heisenberg uncertainty principle?
It's gonna confuse me. My brain is like toast.
I still have to think about.
I'll tell you what, because I gave you homework this weekend in addition to your lab report, I will not make you learn about the Heisenberg uncertainty principle right now. The electron dance is not completed yet. They're doing it today. I don't know what you're talking about, Kevin. Man, my computer's just really slow today.